Hello, Physics 40S. We now have an example of a moving conductor in a magnetic field. So we have a conductor moves in a magnetic field of 0.58 Tesla into the page. So here's the drawing. We have the magnetic field drawn going into the page here. Now we have a conductive track in which there's a conductor resting, and this conductor is going to be pushed along by some force. Maybe it's the wind or water or something. It's going to push it along this track, and if the conductor is moving with a velocity of 15 centimeters per second right, what is the induced EMF and direction of current? So we're saying, hey, we're going to push this along. How much EMF can we expect if we have this strength of a magnetic field and we're going to move this wire at this speed? Okay, so now we do know that the track is separated by a distance here of 20 centimeters. Okay, so that means, yes, the conductor might be longer and might extend over, and even if it's still in the magnetic field, there might be some induction here. But we're going to be limited by where this conductor is resting on the track, because this is also a conductive material. So we've got a little bit of a loop going here that we're interested in, because obviously the track is not connected, it extends out here. So we're not going to get any current flowing that way. If we can induce some kind of a potential difference in this conductor due to a moving wire in the magnetic field, then we can get current flowing in the closed loop. If you remember from our DC circuits unit, we needed a closed loop to get current flow. Okay, so we want to find the EMF and the direction of the current. So our E will be equal to Blv sine theta. Now we are moving perpendicular, so that means that we have a sine of 90 degrees, so this goes to 1, so I don't really need to include that, or you can if you want to. There's nothing wrong with putting that in. Our magnetic field strength, 0.58. Our lengths. Now, doesn't matter how long the actual conductor is, it's just how much of it is going to be contained in creating that potential difference in our loop. So it would be 0.2, changing that into meters instead of 20 centimeters. I want to put that in meters. And then it's moving at 15 centimeters per second. Okay, so again, why do we do this to you? We always seem to be giving you things in centimeters. You got to change that quickly. 0.15 meters per second. Okay, so make sure you're putting that in here too. All right, which means that the induced EMF, not very great, but 0.0174 volts would be induced with that small amount of movement. Now, what about the direction of the current? So we know that we have this wire, and if you remember, I said that in the previous video, if I consider electrons sitting in here, these electrons are moving through the magnetic field. So I'm going to use the hand rule that dealt with the conductors, or not the conductors, sorry, the charges. So I'm going to use my left hand because I'm looking at the electrons. They have a velocity this way. The fingers are going into the page because of the magnetic field, and my palm is facing in this direction, which means there's a force on the electrons that's going to push them along here, and that's going to create a negative end here and a positive end here. So we're not really looking for the current yet. I'm just looking for the potential difference. Okay, so I've used hand rule 3B to find the direction of the force. That was the force on a moving charge. And that's allowed me to develop the direction, or the negative and the positive end of the potential difference. And then in order to find the current in this external loop, that would tell me that we're going to leave from the positive and go towards the negative. Now remember, electrons would be flowing this way, but conventional current, because we're stuck with conventional current, I would indicate that it is flowing in that direction. So if you did draw that the electrons would go the other way, that would be acceptable, but just make sure that you've labeled that as the electrons, conventional current as the flow of the positive charge, even though the positive doesn't move. Okay, so we would have clockwise conventional current, counterclockwise electron flow. So I would say that here, direction of the current, we have clockwise current. Now a little bit of review from before. If the resistance in the conductor is 5 ohms, how much current will flow? Hopefully you remember from our unit a couple of months ago, now it seems, that I was equal to V over R, which is just Ohm's law rearranged. And we figured out that we had 0.0174 volts. We divide that by the resistance of 5 ohms, and we're going to have a very small current, 0.00348 amperes. And then even more review, how much energy is produced if the conductor moves for 10 seconds. Now, if you remember, energy was equal to power times time. So now I need a new equation for power, and power, one of the ones we could use was V times I. So I'm going to replace power with V times I, multiply that by our time. So I have my 0.0174. Of course, I could have used a different equation for power. I could have used I squared R or V squared over R, whichever you prefer, 0.00348. and times 10 seconds. So that tells me that I'm going to produce 6.06 times 10 to the negative 4 joules of energy. Now, maybe not the most efficient way to generate energy, but it is one possible way. Now, this E here is representing energy, not EMF. So that's why I should be a little more careful about doing kind of a cursive E versus a square E. Okay, thank you very much.